Hello and welcome to the C for Beginners programming class. My name is Jason Fedden and I will be your instructor. I want to thank you for signing up for this course. It's going to be a ton of fun and I'm going to do my best to motivate you and help you learn all about the C programming language. Let's get started. First, I want to tell you a little bit about myself. I have a Master's of Science in Computer Science from Binghamton University, and I also have a Bachelor's of Science in Computer Science from SUNY Oswego. I received my Master's in 2001. I've been a software developer for over 16 years. I've been an online instructor for over 11 years. I've instructed over 20 different classes, ranging from everything from object-oriented programming to compiler theory. I have a vast amount of experience with programming and computer science in general. I've been working with the C programming language for over 16 years. Basically, as soon as I got my first job, I started writing C code. I've also created beginner C and advanced C classes at multiple universities. So I have a good amount of experience with curriculum and presenting C concepts to students. I've been a software developer at Xerox Corporation for around 10 to 12 years. While I've been working here, I have been writing C code mainly and also some C++ code. We run our entire source code repository on the Linux platform, and we write real-time code. I mainly concentrate on object-oriented languages and mobile programming. This is what I love to do. So things like C++ and Java. But the C language is really what I have my expertise in. I also focus on writing high-quality code. This is a vital, important concept that I'm going to emphasize throughout the course. I want you guys to focus on writing good code. Not just writing code that works, but writing good code that will help the maintenance of the program be much easier. So some of the topics we're going to cover in the class include the following. And by the way, when we cover these topics, I'm going to provide lecture material. I'm going to provide hands-on exercises. I'm going to provide assessments. I'm going to walk you through code and programming concepts as I'm editing it in an integrated development environment. So it's going to be really hands-on. We're first going to talk about C in general, give you a little overview of it. I'm going to tell you how the C programming language is very efficient. It's also portable. You can write it across multiple platforms. It has a lot of power and flexibility, and it's programmer-oriented. I also provide you a short history of C just to give some context. We'll follow that up by describing some of the common language features of C. C is an imperative language. This is the most modern type of language. It's organized around functions. It has a module design. It's a structured programming language. And you can also have top-down planning when you're writing your code. The advantages of using C we'll focus on. C is great for small, fast programs. It's very reliable, very easy to learn, and very easy to understand. If you were to take a C program from a fellow peer or fellow developer, you would be able to follow it pretty quickly. We're going to use a modern cross-platform integrated development environment, which is Microsoft Visual Studio Code. You can use this on multiple platforms from Mac to Linux to Windows. And we're going to be doing all of our developing using this IDE. We're going to edit code. We're going to also use the IDE to debug our code, which is very important. And so this will be presented as one of the concepts. I'll kind of walk you through the environment and show you how to use the tool. We're first going to start off with basic C concepts. I'm going to describe to you what a C program looks like and give you an example. I'm going to show you the structure of a basic C program. We'll talk about how you can provide comments in your code and also basic output using the printf function. We'll go through a hello world example and also have you write your first program in C. We'll follow that up with talking about makefiles. We won't go into a lot of details about makefiles, but I want to touch on it to help you understand how you can use this tool to build and compile your code. We're going to talk about the most basic programming concept there is, which is creating and using variables. Variables is the idea of associating memory, data in memory for your program with a name. And you're going to create many variables and many different statements in your code. We'll talk about data types, which includes the int, float, double, and char data types. And then later in the class, we'll talk about more advanced data types like enums and then providing your own data types by using a typedef keyword. I'll provide information on basic operators. These are things like doing addition or subtraction, math operators. It also includes logical operators like and or. This would be in kind of like decision statements. We'll talk about how you can assign data to a variable using an assignment operator. Making decisions in your code, very important programming concept. We'll touch on this. These are called conditional statements. These are keywords like if and switch. We'll provide examples and go through the various constructs of this. Follow that up with talking about repeating code, mainly looping. The big looping constructs in C are for while and do while. They're all the same, they're just a little different syntax. We're going to talk about how you can store data and categorize data to different using arrays. So we'll discuss how you can define initialize arrays and then multi-dimensional arrays, which is kind of like a matrix, spreadsheet type of concept. Functions. Functions are one of the biggest, most important concepts related to the C programming language. Everything should be used and organized around a function. This is referred to as module type programming. You're going to learn how to declare a function, how to use it, how to pass data to it, how to return data from it. We'll also talk about more advanced concepts like call by value and call by reference. Debugging. Debugging is a vital concept and essential for all programmers. It's this idea of finding and fixing your errors. We're going to discuss the call stack, which can show you if your program crashes, where it crashed. Very important concept. I'll provide you with common mistakes that many C programmers make, so that if you do see these mistakes, you understand how to fix them. And then the compiler. The compiler will check your code to make sure it's syntactically correct. And if it's not, it will give you error messages or warnings. You need to understand what the compiler is telling you. So we'll talk about the compiler messages and how to understand them. We're going to discuss structs. You're going to learn all about structs, which is similar in arrays in that it stores data. It's a data structure. We're going to discuss how you can initialize structs, how there's this concept of nested structures. For those of you that are familiar with objects, it can be kind of relatable to that, but is not as robust. Character strings, which is essentially a string in C, alphanumeric characters inside double quotes. This is one of the basic data types, but it's thought of as an array in C. It's a little different concept. We're going to go through that. We're going to talk about some of the operations you can perform on strings and so forth. Pointers. Pointers are probably going to be our most important concept in this entire course. So we're going to spend a lot of time on it. Pointers is this concept in C where you have to manage your own memory. It may be a non-familiar concept to you if you programmed in other languages because this is usually done for you. Specifically, if you program Java or C#, you don't have to worry about pointers. In C, you have to worry about managing your own memory. So pointers are a big deal. I'm going to tell you how you can define and use pointers, how you can use them with functions and arrays, how you can call different standard library calls to create memory, and also how you can dereference pointers. It is an important concept, like I said, and we're going to spend a lot of time on this. I'm going to provide you with a lot of examples, a lot of real-world type scenarios, so that pointers are really driven into your brain because you can't use the C programming language without fully understanding pointers. We'll spend a lot of time on this. The preprocessor we're going to learn about. This is a step that happens before the compiler. Specifically, there are directives that you need to understand, like define and include. We'll go through that. We're going to go through input and output, how you can read and write data to the console. We've talked about printf. We're going to go in a little more detail into that by using getchar and scanf, format specifiers, things like that. We're also going to talk about how you can read and write data to a file. This is another sort of important concept when you're writing code. It's a way of storing data. There are many different file operations in C, and we're going to discuss some of those. C is a very low-level language in that it can do a lot of things efficiently and fast, and file writing and reading is at that low level. You can interact with the operating system pretty nicely. There's a standard C library that comes with the C programming language where there's a lot of different functions that you can utilize. There's string functions, string manipulation functions. There's math functions, utility functions. We're going to go through all of these basic functions that you can use that help you write code more efficiently. Just like different libraries in other languages, C is going to provide you with some of the basics. Again, in order to write and read from files, manipulating strings if you want to get cosine and tangent for math functions. That's all provided for you by the language. We're going to learn about that. And those are the main topics that we're going to cover, beginning topics. We're not going to go into any advanced topics yet, but we're going to cover the basics, the fundamentals. So at the end of this course, you should be able to write beginner C programs, understand the fundamental aspects of the C language, know how to provide input and output, do file and I/O, drill down the concept of pointers, etc. You're also going to, as we go through this course, focus on writing high quality code, efficient code. This is very, very important. Again, it affects the maintenance phases of the software lifecycle. So if you want to find and fix your errors, it's much easier to do that if you have high quality code. So as we go through examples, as we learn these concepts, we're going to learn how to do it the right way. We're going to learn how to make things modularized so that things are grouped into functions. We're going to make sure that in our different files, we have low dependencies, low couplings, so that they don't affect one another. When you have a lot of dependencies in your code, you can it's much easier to find and fix your bugs. And if you ever want to add new functions or add new code to a program, it's much easier to do that if it's modularized, if it's organized in functions. So we're going to focus on this concept of writing high quality code. We're not just going to get things to work. We're going to do it the right way. At the end of the course, you'll be able to find and fix your own errors. An essential part of becoming a good programmer is problem solving. We're going to focus on problem solving techniques and how to debug your code and how for you to become an efficient problem solver. This includes understanding the compiler messages. It understands how to run a debugger, how to use the call stack, all these nice things. Problem solving is going to be drilled in all lectures. You're going to understand the fundamental aspects of the C programming language, topics I mentioned previously. This is going to be basic C stuff. Lastly, you're going to have fun. I'm going to do my best to motivate you. I'm going to have fun and exciting examples. I don't want you to fall asleep during lectures or exercises, so I'm going to make them lively, and I'm going to do my best to motivate you and help you throughout this course. So I'm looking forward to it. I'm really excited, and I hope everybody is ready to learn a lot about the C programming language. Thank you. Hello and welcome back. Let's talk about the fundamentals of a program. Since this is a beginning programming class, specifically we're going to be talking about C. Before you can understand even a programming language, you need to understand what a program is. So I want to describe some basic concepts to you before we get started in the details of C. Computers are very dumb machines. You guys are, I'm sure, more than not familiar with what a computer can do and what it does. Specifically though, under the hood and what's going on in terms of when you click your browser, when you click your different applications that you use, what's happening under the hood is there is some kind of program that's running, and that program is telling the computer what to do. Computers are really dumb. They only do what they're told to. So the basic operations of a computer will form what is known as the computer's instruction set. Right? And an instruction set, if you can kind of think about that, it's just how it's going to do something. So we need to tell this computer how it's going to do. We do it in the form of a program. At an even lower level, each computer has what's called an instruction set. And an instruction set is basically the instructions on the CPU, the processor of the computer. So to solve a problem using a computer, by telling it what to do, you provide this solution by sending these instructions to the instruction set. So that's what's happening when you write a computer program, is you're sending specific instructions to solve a specific problem via commands to the CPU, the processor, okay? And the approach or method that is used to solve the problem is known as an algorithm. So for you guys that understand math, an algorithm is just, again, how you're solving a problem. So for example, if you were to create an entire program and all it does is test whether or not a user enters an odd or even number, what would be described as the algorithm itself is the test, whether or not the number is even or odd. That's the algorithm. The statements that solve the problem in its entirety becomes the program. And we'll discuss this concept in algorithm. Algorithm is even more kind of related to module programming. So we'll talk about that when we talk more about the details of C. But again, I want to let you understand what you're doing when you're writing code. What's going on at the very, very lowest layer. you're going to write these algorithms that are contained inside of a program. So to write a program, you're going to need to properly write the instructions to implement the algorithm. These instructions can be expressed in any kind of statements of a particular language, programming language. So we're going to focus on C for this class, but I'm sure you've heard of other programming languages like Java, C++, Objective-C is used in iOS applications, but actually more now it's Swift is used. But there's all these different programming languages that you can learn that essentially are going to allow you to send instructions to the CPU in the form of algorithms and statements. Also, want to talk about some basic terminology. The CPU, the central processing unit. This is the brain of the computer. This is where most of the work is being done. This is where instructions are executed. Memory. You often hear this term memory, and students often get memory very confused with the hard drive. Memory is not the same as the hard drive, right? Memory is often referred to as RAM, which is random access memory. All of the data that's stored in memory, it's a separate hardware component. It's not an actual disk drive. All of the data in a program is stored in memory, this separate hardware component. So it stores the data of the program while it's running. And we're going to talk about variables and what they mean, but a program needs to have data in order to perform calculations, in order to do algorithms. That data is going to be stored in RAM, memory. The reason we store it in memory as opposed to storing it on a hard drive is that memory is much faster. It allows the program to run much quicker. But memory is also usually not persistent across reboots, another kind of clarification. But you should understand just this term RAM. It means memory. It's the variables and the data in the program itself where it's stored. It's a separate hardware component than the hard drive. The hardware drive is something you buy with the computer that's permanent storage. This is usually really, really large, contains gigabytes, terabytes of data. This stores files that may be resources of a program. And when you turn the computer off and turn it back on, those files are still there. When you turn the computer off and on and the program actually stops executing and there's nothing in RAM. So understand the difference between RAM and hard drive. It's an important concept. Again, think of RAM as related to programs, hard drive related to permanent storage, and we usually put resources on there. We'll have operating system files, all sorts of different program resources. An operating system is developed to basically make your life a lot easier when you want to use the computer. Because at a very low level, a computer is just doing what it's told, and it's just instructions on using an instruction set, it would be very, very difficult to use if you were to have to understand all these instructions. So there's a program called an operating system that makes it easier for a user to use a computer. It controls all the operation of the computer, handles all the input and output via hardware, so it understands how to interact with a keyboard, a mouse, a monitor. It also manages the computer's resources, handles execution of different applications. An operating system is a completely separate class. There's a lot that goes into an operating system, but understand the basics of it. It's just allowing you to use your computer in an easier manner. Some examples of very common operating systems are things like Windows, right? Everybody uses Windows, Windows 10, Windows XP, whatever the case may be. Linux, Unix, which we'll talk more about when we talk about the history of C. Android is an operating system for mobile devices. iOS. These are specific programs that are very large that may contain many different programs that interact and make your life a lot easier with interacting with the computer. The FEX execution cycle. This is the life cycle of CPU. I only mention this because, again, we're just describing basic terminology. This is how, when you send instructions to a computer, the CPU, what's actually happening is you're fetching the instructions from memory because that's the program, and then you're going to execute that on the CPU. And it's this kind of loop. You're doing it over and over and over. You're repeating it. And if you've ever heard of the term gigahertz, a gigahertz CPU can do about 1 billion times a second, 1 billion instructions a second. So you can kind of imagine what's going on when you're running a computer with this fetch execution lifecycle. And here's a little illustration that I took from an image on the internet that shows you this fetch execution cycle a little bit clearer. What's going down when you're interacting with the CPU and these instructions. What's happening is you're grabbing from RAM And RAM, remember, contains programs data. You're grabbing data there for instructions, and you're constantly decoding the data, which is stored in registers in RAM, and then executing it on different parts of the CPU, either the control unit or the ALU. It's a loop, though. It just repeats over and over and over. And again, for CPUs nowadays, you get a billion times a second. So when we talk about C programs and writing C programs, at the very low level, underneath everything, we're just interacting with the CPU via our higher level programming language. So a higher level programming language. Higher level programming languages make it easier to write programs. Now, if we were to have to, again, understand all these instructions on the CPU, it'd be very difficult to write. And to understand all the instructions, that usually means it's an assembly language. If you've ever heard the term assembly language, it just means you're writing a program at a very low level, where it's such a low level that you understand the instruction set. And you can imagine that if you were to write all of your programs with all these instructions, it would be very inefficient and very difficult to write a program. So higher level programming languages are the opposite of an assembly language. It's a much higher level. An example is C. C is a higher level programming language. It describes the actions that the program is going to perform in a much more abstract way. You don't have to memorize the instructions on the CPU. You just understand the language itself, and you solve problems through these algorithms. It looks much more like the English language. It's much more easier to understand. If you were to look at an assembly language, what you're going to see is move commands with registers, with numbers, basically just numeric statements. And by using a higher level language like C, you don't have to worry about any of this. You don't have to worry about the instruction set. You don't have to worry about assembly language statements. So it's much more efficient, and it's much easier to accomplish and solve problems. And so we're going to study C as our higher level programming languages, but other examples would be Java, Objective-C, things I mentioned. These are high level programming languages that make your life a lot easier and are much more efficient. In addition to these higher level programming languages, if you have this language that's more abstract, you have to be able to take that language and then run it on a CPU. You have to convert it essentially to instructions that the CPU understands. And so this is where a compiler comes into play. Often when you write code in programming, you're going to use a compiler that translates this high-level language, source code, into detailed machine language instructions, basically assembly language. So you're going to write a program that's going to do high-level, more abstract thinking, and then the compiler is going to generate all the millions of instructions that go to the CPU on the instruction set. So we're going to use a compiler in this class to do exactly this. We're going to write source code in a much high-level abstract form, and then we're going to run a program called a compiler to convert that code into something that the CPU understands. Nice. The other thing about compilers is they're also going to check whether or not your program has valid syntax. So when you write code, you have to follow the rules of the language. The rules of the language are essentially the syntax, whether or not you have a semicolon at the end of a statement, whether or not you use certain keywords. If you do these things incorrectly, you're not going to be able to run your program. So the compiler is going to find all of these errors, and it's going to tell you and report back to you and say, hey, you didn't write your code correctly. You have to fix them before we're going to actually convert this stuff to the instruction set on the CPU. So we're going to get familiar with compilers in a general sense, how to use them, how to understand what they're telling us. High-level languages are much easier to learn, much easier to program in than machine languages. That's the gist of this slide right now, is that by utilizing a language like C, it's going to be much more efficient and easier. When we write a program, we're going to actually perform multiple steps. And I found this illustration that really describes the steps in a really nice way. So I took this from a book. It's a basic set of steps when you write any kind of program. From the first step of defining the program objectives, understanding the requirements, to maintaining and modifying the program. So let's just walk through these steps real quick, and you're going to be finding that you're going to be doing this in this class. You're going to be, when you start to write a program, you're going to follow all of these steps. The first step is going to be to define the program objectives. This is where you're going to understand the requirements. You cannot start writing code unless you understand what you need to do. So you need to get a clear idea of what you want to accomplish in this step. After you understand the requirements, you're then going to start to design the code. When you design the code, this is how the above how the code is going to meet the requirements. What's the user interface going to look like if it's required? How are you going to organize your program? Are you going to create different functions and try to create different algorithms and so forth? Then you're going to start implementing the code. This is where you actually write the code and put it into an editor in an integrated development environment. You translate the design to the syntax of the programming language, in this case C. Understand the rules of the C language. So you can use any text editor. We're going to actually use something called code blocks. You'll typically want to use something more than a text editor, something called an IDE, which we'll talk about. Once you're done writing the code, you have to compile it because it needs to convert it, the source code, to the low-level language. We talked about this already, so this is a pretty basic step. And then you run the program. Running the program is executing it, is using it. And then that's going to be the fifth step. After you run the program, you're not done, because even though you wrote the code and it may be meet the requirements of the language, it might not do what it's intended to do. So you have to test it, and you have to find and fix your errors. So just because a program is running doesn't mean it works. I get a lot of students to say, hey, it compiled, I'm done. No, you have to make sure that when you run it, it meets the requirements and it does what you think it's going to do. So you have to constantly test. And you'll be performing steps 1 through 6 over and over and over again. You're going to be finding that you're going to be writing code, testing, writing code, testing, writing code, testing. And typically when you do this, you want to do it in very small chunks. You want to write 2 lines of code, test, another 2 lines of code, test, and so forth. So you need to test and debug. Debugging is another concept. We'll have many lectures on debugging, but this is when you find and fix your programming errors. There are certain techniques you can do, certain tools you can use that help you find these errors. And you'll learn a ton by testing and debugging, because you always can learn a great amount of information by making mistakes. And that's going to be normal. You're going to compile, and the program's not going to do what you set it to. And you're going to learn from that. And that's what we're going to do in this class. I'm not just going to show you the correct way to do things. I'm going to show you the wrong way to do things, and then you're going to see why this is wrong. The last step is maintenance. This is when the programs are released and then used by many people, but still may have bugs. So for example, when Windows 10 is released, you'll notice that it still has bugs or still crashes. And so you're constantly getting updates. And when you get those updates, that's called maintaining the program. So just because you're done writing the code and releasing it to the public, it doesn't mean you're done maintaining it. Maintenance is often the most expensive phase, most expensive step, because when you release a program, it could be out there for 5 or 10 years. You're going to have to fix these bugs so that your customers are happy. You may also want to add new features to keep it up to date in the market. So maintenance is really important as well. Maintenance happens after you release the product to the customer. So for all of these steps, you may jump around, execute steps in different order, depending on what programming methodology. That's a whole other lecture as well. You're not always going to necessarily do these steps in a kind of waterfall approach where you start at the beginning and end at the last step. You may be designing and then going back and doing your testing and then going back and redesigning and so forth. So you're going to be jumping around, all depending on what's the most practical. From my experience, many new programmers and many of the classes in Udemy are ignoring steps 1 and 2 and going directly to writing the code. They're showing you how to write the code, but they're not showing you why you're writing the code. So this is a big mistake. When you start to write code, you need to understand the concepts. You need to understand the requirements. And you can get away with this in really tiny programs, but with larger programs, you're going to need to fully focus on design. Okay? So the larger and the more complex the program is, the more planning it requires. You should develop the habit of planning before coding. Do not just dive in. And you're going to notice from the lectures in this class that I do a lot of planning. I'm going to tell you in the challenges, when you start to write some code, that what you need to do and how you should design it. Right? Because this is going to make it easier for you to actually implement the code, which is step 3. So keep that in mind. You can often plan things by writing things down on paper. There's all sorts of nice documentation, designing languages out there and things you can use. But you always want to basically plan efficiently. And then as you're coding, I mentioned this earlier, but this is another very, very important concept. You always want to work in small steps, divide and conquer, and you want to constantly test. You do not want to write 100 lines of code and then say, oh, I'm done, let me go test. Right? Because now, if it doesn't work, there could be an error in any 100 lines of code. It's going to be much harder to solve that problem. But if you write code in little chunks, 5 lines of code, test it. Then write another 5 lines of code, test it. It's going to be much easier to find and fix your errors. So let's focus on divide and conquer when we write our code in this class. I hope this helped. Again, this is just some basics. I wanted to provide some basic terminology. A lot of you may already know a lot of this information, but when you're learning a programming language, you have to understand these basics. Thank you. Hello and welcome back. In this lecture, I want to discuss some of the specific features related to the C programming language. So we know all the advantages of C. I talked about that kind of ad nauseum. We know that C produces compact and efficient programs. That is a language feature, though. That's important. It's one of the most important programming languages and will continue to be so. We know all of this. So I just, again, want to reiterate it. But the main features of the C language are that they're efficient, portable, powerful and flexible, and programmer-oriented. And we're going to cover these in more detail, what this means. But these are important characteristics of C. We need to understand them, again, in order to understand how to write the code in this language. So what does efficiency and portability mean? Well, C is an efficient language. It takes advantage of all the capabilities of current computers. It's very compact programs written in C. They're very fast and compact. I talked earlier about how the mapping of C and C statements to instructions in assembly language is very efficient. This is one of the reasons it's so fast. One of the complaints about Java in the past used to be, hey, Java's really slow. Well, you don't have this problem with C. When you write a program in C, it runs fast, it's very compact. So that's a language feature. That's an efficiency. Programmers can fine-tune their programs to make them even more efficient because it is such low level. They can use more efficient use of memory. You can't do things like this in Java. Java has its own garbage collector, and you can't manipulate the memory to be more efficient. So C is an efficient language, and it's a portable language. So I touched on this briefly in a previous lecture, but this is important because what this means is if you write a C program on one operating system, you can run it on another operating system without modifying it. One of the issues when writing code in today's world is sometimes it's not going to work unless you write it in multiple languages or modify it extensively. So for example, if you write an Android application for an Android phone, it's not going to work on an iOS phone. Right? You don't have those types of issues with C. You write C and it will work on all sorts of different hardware, all sorts of different operating systems. In fact, C is the leader in portability, this capability, and the compilers are easily available. You can get a compiler on Windows, Linux, no problem. Linux, Unix systems typically come with a C compiler, so you don't even have to download it when you're on Linux, Unix. Same with the Macintosh. So you can start writing C programs immediately. No external downloads. They're also available, obviously, for Windows, but typically for Windows, you will have to download a compiler. And we're going to be doing that when we download our required software. So there's a good chance that you get a C compiler for any device that you're using. You could probably get a C compiler also for an Android device or an iOS device. Really low-level micro or mini computers as well, like processors and automobiles. It's also very flexible, which is important, and it's also very powerful. So the Unix, Linux kernels are written in C. What is a kernel? Well, we know Unix and Linux is an operating system. We know an operating system will help you more efficiently, use a computer, and it controls a lot of the aspects of interacting with hardware and so forth. The kernel is the brain of the operating system. So just like a CPU is the brain of a computer, a kernel is where really all the brain and knowledge of the operating system goes. So it typically contains interfaces of the hardware and the kernel. It manages memory. It does all sorts of different things. And that is all written in C. So that can tell you the powerful aspect of the language. If the kernel of an operating system is written in that language is powerful. So many compilers and interpreters for other languages are built on C or have been written in C. So if that doesn't tell you the powerful nature of the language, I don't know what will. But Fortran, Perl, Python, any compilers that are written in those type of languages are written in C. So C programs have been used for solving physics and engineering problems, and even for animating special effects for movies. Widely used for many different things. Flexibility is also important, especially when you're a developer and you're writing this code. You want to be able to do things in different ways. You want to be able to solve a problem in many ways. More flexibility, typically, the better. However, there is a trade-off between flexibility and performance. So you want to so sometimes it's catchy when you're designing a language, but C was designed to be flexible and is very flexible. So you can do just about everything you want in a C program. You can write all different application types, and you can also manage memory and do different things that many other languages restrict you on. There is a trade-off because sometimes the flexibility causes more bugs or causes developers not to fully understand certain concepts because they may be more complex. But ultimately, flexibility is a good thing, especially if you're a developer that understands the language very well. It's also the basis for more advanced languages such as C++, mentioned that earlier. It's used for developing mobile phone apps in the form of Objective-C. Objective-C is a proprietary language by Apple. Basically, it's C with objects, just like C++, but they decided to write their own language. But it is used in iOS, less and less so, because Swift is being more popular. But it's also easy to learn because of its compactness. It's an ideal first language to learn if you want to be a programmer. And I think I've given the rationale for that pretty good. You're going to acquire sufficient knowledge for practical application development very quickly and very easily. So that's why it's a good first one to learn. And that's what you're going to notice in this class is, wow, now that I learned C, wow, it's much easier to learn Java. It's much easier to learn PHP. It's a lot easier to learn these other languages because it has everything that those languages have, and it's very easy to learn. It's programmer-oriented. That's a language feature. It fulfills the needs of the programmers. I told you how Dennis Ritchie, when he created the language, wanted to make it more developer-focused. And he did that. He accomplished that goal. It gives you direct access to hardware. It enables you to direct access to memory and manage your own memory. So the flexibility comes into play when it is programmer-oriented. In Java, you can't do a lot of these things like manage your own memory. C also has many other capabilities that allow flexibility. And I think that flexibility allows be more programmer-oriented because programmers like that. They like that flexibility. They don't want to be told what to do. It contains a large selection of operators, which allow you to express yourself succinctly. Now, this means we don't know what an operator is yet, but an operator can be things like adding and subtracting mathematical operators or assignment operators, assigning data to memory. And the more operators you have, allow you to express yourself more in your code. And so a language feature with being more program-oriented is this list of operators, which we'll talk about in a lot more detail. It's less strict than most languages, limiting what you can do. Kind of talked about this already. I mentioned the trade-off with this, flexibility versus strictness. It's an advantage in that you can do things in many different ways. However, it could be a danger because it's more prone to error. Programmers, especially with something like pointers. So the fact that you can manage your own memory in C is very flexible, but it's also very complicated sometimes. And as a result, many programmers introduce bugs into programs. Now, Java doesn't allow you to manage your memory, but it's also less flexible, but it also reduces your bugs in your program. So there's a trade-off. You want to basically have flexibility by also allowing things to be less complex. C gives you more freedom, but also puts more responsibility on the developer. And that's why it's program-oriented. C implementations have a large library of useful C functions, so you don't have to write everything in C if you want to do something. Programming languages would typically contain other program functionality that comes with the language. So, for example, if you want to read input from the user, you don't want to write low-level C code to do that. There will be code in C that already does it for you, and you just reuse that code. And that's usually encapsulated in something called a library. And so C has all sorts of library functions to read data from the keyboard, to write data to files, to create all sorts of nice things with different processes and thread. I mean, all sorts of nice things. So the fact that that a lot of implementation comes with the language and you don't have to actually implement it yourself, you just have to learn how to use the libraries, is very advantageous and very programmer-oriented. Some other features of C are it provides low-level features that are generally provided by the lower-level languages. We talked about this. But again, the best example of this is memory management, direct access to memory. Programs can be manipulated using bits. Wow, if that's not low level, I don't know what is. It is the ability to manage memory representation at a bit level. Bits and bytes are how we actually store data on computers, provides a wide variety of bit manipulation operators. Again, something in the language that we'll talk about in more detail. Pointers play a big role in C. This is a concept that you may have heard of before, you may not have heard of, but it's related to memory management. We're going to have many lectures on pointers. But it is a very, very important feature of C that you should be familiar with at the very high level. C, manage memory. C, pointers. Often when you think of the C programming language, first thing you think of is pointers. And all this is direct access to memory. Disadvantages of C. We talked about that flexibility trade-off, flexibility versus freedom. It also requires added responsibility. Some view this as a disadvantage. Some view that pointers are abused. And as a result, many people write bad C programs. Well, yeah, if you give somebody a tool to do something and they do it incorrectly, who's at fault? It's kind of, again, do you want to restrict that tool because it's abused, or do you want to allow that tool to allow flexibility? So you can often be more flexible, but it's at the risk of making more errors, and a lot of times these errors are very difficult to find and trace, especially if they're memory stuff. So that can be a problem. Other things, because of its wealth of operators and its conciseness, it makes the language difficult to read and follow sometimes. For the most part, C is very easily readable. But if you use a lot of these different operators, that can make it more complex. So there's an opportunity to write obscure code, but any language can be badly written. So you can use the English language when you speak and you can have bad grammar. It's no different when you use a programming language. But some say with C it's a disadvantage because of all these operators. It could be if you use it incorrectly, it can be harder to follow the code. So just to summarize, this is a nice illustration again I found on the web that I'd like to provide you with. The core features of the C language: fast and efficient, portable, a lot of nice libraries where you can reuse code and you don't have to do things on your own. Modularity, talked about earlier, but this is the idea of organizing your code around functions. Easy to extend, and then all of these powerful operators that allow you to do things. So a lot of nice features, and in most of the features that we just talked about are in many modern languages because they're built off of C. Hello and welcome back. In this lecture, I'd like to talk about what goes into creating a C program. So there are 4 fundamental tasks in the creation of any C program. And what these tasks include editing, compiling, linking, and executing. All right, we talked about the different steps that you'll employ when you write a C program in terms of you're going to understand requirements, you're going to design your code, you're then going to write your code, you're then going to test and debug it and so forth, and then maintain it. This is what I'm talking about here is what you actually need to do after when you start to write a program. We kind of talked about editing, compiling, but linking and executing are also important. And what I want to talk about here is the details of this. So these tasks are going to become second nature to you because you're going to be doing it every time you write a C program. You're going to be editing your source code. You're then going to be compiling. You're then going to be linking, and then you're going to be running. You're going to be doing this very, very often. So the processes of editing, compiling, linking, and executing are the same for developing programs in any environment with any compiled language. This is not unique to C. If you're writing Java, a Java program, you're going to write the source code. You're going to compile the source code. Linking you might not be as aware of in Java, but it's going to do some kind of linking. And we'll talk about what linking is. And then you're going to run the program. You're going to be doing all of this. What I'm describing here, again, is how it's done in C. So editing is exactly what you would think it is. It's the process of creating and modifying the actual code, the C source code. The C source code is going to be inside of a file, and it's going to contain all of the statements and all the instructions that you write. All C source code files end with the .c extension, and that's how you can identify that it's a source code file. Before that .c extension is going to be called the base name. You want to have your file names be meaningful. If you write a C program that adds 2 numbers, you may have a file called add.c that contains the source code. And remember that a C program, in most C programs, are going to have many, many different files. So your files should have good names. But the way that you can identify C source code is the .c extension. They all contain the .c extension. Now, when we edit our code for this class, we're going to use an integrated development environment. We're not just going to use a simple editor. An example of a simple editor would be something like WordPad. We're going to use something that has an editor, but also has many other things that help you write your code more efficiently. The IDE, and this is referred to as an IDE, Integrated Development Environment. The one that we're going to use for this class is code blocks. I'm going to cover in detail, but we're going to use code blocks for the editing task. But you can use whatever you want. If you want to use Notepad, if you want to use something even more minuscule, you can. Atom, there's Visual Studio IDEs, but the one we're going to cover in here is how to edit your code and code blocks. And this is a nice IDE, and the reason I chose it, we'll talk about in more detail, but it is cross-platform and easy to use. So editing is the basic process, writing the code. Compiling, we know what a compiler does. It just takes that high-level language code and converts it to machine language, and it also detects and finds errors in your code. After you edit your code, you're going to run the compiler. So the input to the compiler is going to be all of your source code, all of your .c files, everything that you're editing. And again, a C program can have many source files. But the input to the compiler are these source files. Compilation itself, converting this code, is a two-stage process. The first stage is called the pre-processing phase, during which your code may be modified or added to. And the second stage is the actual compilation. It generates the assembly language code. And we'll talk about this in more detail, this pre-processing phase, but you just need to know now that there's two stages when you do compilation. The one that we're going to focus on, or the one that's easy to understand, is the generation of the object code. So the compiler is going to look at each statement, and it's going to make sure that the syntax is correct and that the semantics of the language is met. Syntax is to make sure that the structure of the code is right, that you have semicolons at the end of the statement, that you're using data types, that you're following the rules of the language. Semantics is the meaning of the words. So if you use an if keyword, that's a condition. Semantics happen in the compilation phase by creating a symbol table and so forth. But the compiler is important. It's going to generate this object code. It's going to tell you if you have any errors in your syntax. It can also sometimes recognize whether or not you have dead code, where basically code's not being used. It does not find logic errors. It only finds syntax errors. Again, syntax is the rules of the language. Logic errors are the meaning. Like if you made a mistake in logic, you may make a mistake in the functionality. So your code can run, it can compile, but it may not work as intended. And this is referred to as a logic error. The compiler is not going to tell you if you have a logic error. If you meant to ask the user for a number instead of a character, a string, or you ask the user for their last name before their first name, that's a logic error. Compiler is not going to tell you those types of errors. Typical errors reported by the compiler are going to be things like undeclared variables, expression that doesn't conform to the syntax, you don't have the right parentheses, you have, blocks that don't have ending blocks. You're going to become very, very familiar with the compiler errors and what they mean. Hopefully, after you've learned the C language and you run the compiler, you're going to see an error and you're going to be able to fix it immediately. You say, whoops, forgot a syntax, or whoops, forgot a semicolon. Oh, I forgot to provide a right bracket to end that block of code. It's going to become second nature. So after you fix all the errors and your compiling is successful, it's going to translate into assembly language and generate this object code. So the actual object code is a .o file. It's the actual assembly language code that gets run. It has an extension .obj or .o. .obj typically on Windows will be the extension. .o on a Linux or Macintosh system will be the extension. You're going to see that file generated after you compile your code. And that's just the end phase of the compilation. That's the actual assembly language. It's going to be binary. It doesn't look like text. You're not going to be able to look at it. It's just going to have a .o extension. And that's what the compiler generates. The way that you run the compiler in C is you actually use a command. You probably won't need to do this much because the IDE, the editor in the integrated development environment, is going to do it for you by just clicking a menu option. But it's important to know what's going on. So when you issue the compiler command, it's typically using a GNU compiler, which is a GCC command. But at the basic level, you just run a compiler program, either CC or GCC. You run that program and then you specify the input. Remember, the compiler takes as input the source files. You specify the input by using a -c flag and then specifying the source files, one after the other. So examples here are cc-c myprog.c, or if you're using the GNU compiler, which is a popular one, gcc-c. And if you omit the C flag, your program will automatically be linked as well, which is the next step. But really, it's easy to run that compiler if you're at the command line interface. It's even easier if you just use a menu option, which we'll probably be doing in this class. But again, it takes input the C source files. In code blocks, as I mentioned, you're going to be just clicking a menu option and it will automatically compile, link, and then you can click another menu option and it will automatically run. But again, what's going on under the hood is you're actually issuing the compiler command with the -c flag and the input source files. After you compile, you link. Like I said, every programming language has a linking, but a lot of times it's transparent. You won't even know what's happening. In C, the linking process is important because it's not always transparent, but with most modern IDEs today, it is. But I do have to emphasize that it is a little, it is important in C. So after the program has been translated into this .o code, this object code, it then is ready to be linked. The reason we link is if we're using external libraries, we have to grab all those other libraries and put them into one program. So linking is just getting all of the dependencies in place and building an actual executable file. So the .o file is the objects. You then link all the .o's into one executable. And again, this is usually transparent, usually happens automatically when you compile, but again, it may not. And you may have to do a separate command, like a -l or something. But it takes all those object files and builds one executable. And the executable is what you run. So it's going to combine all of those, and then it's also going to combine, and you may have .o's that are additional libraries, that other programs that you may want to use that somebody else wrote, or other libraries that come with the C language. You're going to take all of those and put them together. And the linking phase will also detect and report errors. They're two separate phases. Linking, again, will usually be like redefinition errors, or you're trying to call a function that doesn't exist. So if you don't have that .o file to make up the entire program, you're going to have a linking error. And you'll need to have all the .o's. And again, the .o's may not even be yours. They may come with the C language. They may be part of the standard library, or they may come with another program that somebody else wrote. But you need all those .o's to form one executable. So program libraries support and extend the C language by providing routines to carry out operations that are not part of the language. Input and output libraries are example. Mathematical libraries, string manipulation libraries. This is just the same thing. If you're familiar with the Java program, it's the same thing as the Java API. It's the same thing as packages. It's this concept of I want to write data to a file. I don't want to implement it myself. I'm going to use an existing library that comes with the language. It's still written in C, but it's not part. It's just C comes with that. So there's all sorts of different libraries that we're going to learn about and use. This happens part of the linking phase. So a failure during the linking phase means that once again, you have to go back and edit your source code to make sure that you can find that object file. So a lot of the failures usually mean that you just need to include a file or something like that. This will become second nature as well. Success. If you're done compiling successfully and you're done linking successfully, that will produce an executable file. In a Windows environment, the executable file will have a .exe extension. In Linux and Windows, it will just have by default a.out. You can change the name of a.out to something more meaningful by just issuing something along with the compiler command. But most IDEs and code blocks as well will have a compile and link program in a single operation, and it will produce the executable, and then you can just double click the executable. Or you can run the executable from a command or from a menu option. But no, at the low level, if you're on Linux, you're going to see an a.out by default as your executable. On Windows, you'll see a .exe. A program of any significant size will consist of several source code files. I mentioned this earlier. Each source code file needs the compiler to generate the object file that needs to be linked. The program is much easier to manage by breaking it up into a number of smaller source files. You will want to use many source files, and you don't want a source file that contains 5,000 lines of code. That's not cohesive. That's not easy to manage. So you're going to create files that contain source code, and the source code is going to be specific. It's going to have a specific functionality. It makes it much easier to develop and much easier to debug, and is much more cohesive. So you're going to have many smaller source files. You don't want large source files with thousands of lines of code. And all of these source files are going to make up the entire program. They're all going to have their own .os, and they're all going to be input to the compiler. All of this, these concepts that make up the program essentially are also considered a project. You can think of it as that at a higher level. It's your project. It's your program. After you've finally done all of this and you've linked it and you've got your executable file, you can then run the program. In most IDEs, this is just going to be a menu click. Or you can double click in Windows, you can double click the exe. And if you're on Linux, you just type in a.out. Now, when a.out, you have to have certain permissions, so you have to maybe issue a change mode command. But to run it, you can say ./a.out, and that will run the program from the command line in Linux. But again, usually you don't have to worry about this. So the execution stage is where you run your program. Each of the statements of the program is sequentially executed in turn. If the program requests any data from the user, the program will pause and get that input. It can get the input via the keyboard, or it can get the input via graphical user interface if you have libraries for that in your C code. Results that are displayed by the program appear in a window called the console. And we're going to show you examples of this when we talk about code blocks. But when you run your program, typically you're going to see output. Not always. Sometimes programs will do things that don't produce output, but usually they produce output and you see the output right on the terminal or the console. The execution stage also generates a wide variety of error conditions. So you may produce the wrong output, which is just a logic error, and you have to go back and edit your source code. It may sit there and just do nothing because you have logic issues. And then lastly, it may crash your computer, which is the worst case scenario, which means that you did something really bad in your program and it was so bad that the program just died. Or it actually caused other programs on your operating system to crash your entire computer. Right? So running the actual C application can cause problems. If the program does not perform the intended functionality, then you have to go back and edit the source code. You may have to reorganize or redesign. And this is where we talked about the different steps. This is known as the debugging phase. To find and fix your errors, we're going to have a whole section on debugging because it is that important. I mentioned earlier that one of the best ways to learn is to learn through your errors. You're going to constantly go back and edit source code and debug. The entire process of compiling, linking, and executing the program is repeated until you're done, until you have all the results that you need for the functionality of that code. So here's again another nice illustration I like to provide. This is taken from a book called Beginning C by Horton. But this is the process that you're going to have. You're going to edit your source code. You're going to create a file with a .c extension and a meaningful name. You're going to use an editor to do that, or an IDE, integrated development environment, something like code blocks. You're then going to compile it. The compiler is going to generate an OBJ file, an O file. If it doesn't generate that file, that means you have errors and you have to go back and fix them. After you create the OBJ files, the object files, you then have to link them all together to create an executable file. And you could also have errors in that phase where they're not linked properly. You have to go back and edit your source code. Once you actually have no errors and you have an executable file, you can then run your program. And again, after you run your program, you still may have errors because there could be logic errors. So then you would go back and edit your source code. So this is going to become a repetitive process that you're going to be very familiar with. Edit, compile, link, execute. And this again is typically what you do in all languages. You're going to be doing this over and over and over again until your program meets all of your requirements.